So you can see what is our experiment about. It is to find the orbital periods of the unique orbiter using a planetary CM and 8-inch reflective telescope. So CM stands for complementary metal oxide chemical. Moving on, this will be our way of presentation. Let me tell you more. Uh, the reason we wanted to do this is first thing, first time I was talking about got an experiment. So, which is very nice. So, and the first experiment that you, the reason we did this experiment was, first of all, if you have an experiment, you have to understand how to take off do data, how to analyze it. This is a very simple experiment, which and we want to learn how to analyze. So, how to actually do scientific experiments. So, before we continue, I would like to give you a few insights. So, why does anyone redo an experiment? Make sure that they yes, that's one. The ultimate motivation would be that you would be justifying yourself. You're not going to believe some people who has told it or something. You're going to see actually happening. Now, they say that, okay, these Jupiter moons orbit in some harmonic fashion. That, okay, this is twice of this orbit is, orbital period is twice of this one. But why do, why to believe them? We can just try it out. So, this was one of the motivation. And also to get an insight of experimental view. Imagine uh, when Galileo first saw, the date was I think 7th January 1610. All right, that time there was there was no formal theory of gravity. Also, imagine the time when Galileo had seen those moons, those just saw some four random stars in the sky, and he took his observations. Next slide. Oh, I think I forgot that this photo was taken by. So, yeah, this slide. He took these notes and then he published it. He first thought of them as stars and he repeatedly saw them and concluded that they were not stars and they were in fact moons which were going around Jupiter. And this actually led him to think that okay, Earth is not the center of the universe or solar system. Sun is the one. If Jupiter can carry its moon around Sun, so can Earth. Earth can carry its moon around Sun. That was one strong evidence for heliocentric solar system. And at the same time, you might not know this person. It is Simon Maria. He was a German astronomer. The same around the same time, he also found the same Indian moons, which we call today. And the names which we follow, that is Io, Europa, Callisto, and Ganymede, right? That was actually given by Simon Mack. So, but then the other side of they use the stars in general on given planets. Apart from example Jupiter as well. So given a planet, we usually name them like this is how the general like convention of naming stars of the given planet. Give me the on the experiment. The primary aim of the experiment was obviously to find the orbital period of the brightest, the four moons, the Galileo moons that we have. Callisto. And apart from that, we also went ahead and used some theory, which was like we used Kepler's law to also get the mass of Jupiter. Proceedings already proceeded, or we kind of came out with a rough framework. We had Vasan who made the simulations in Stellarium, and we just made a simulation of 20 days and we saw how we moved more with time. You can see this Europa is here, but these are all labeled. We did this simulation and kind of got an idea that okay, so when we are going to do an experiment, we just is Jupiter and its moons every day, and then somehow try to get information from those events, right? Now, here, as I said, these moons are already labeled, but you look at the moons that we have, then we just write dots, and we have to figure out our own which moon. So the apparatus procedure. So apparatus we used there was an imaging sensor. So now there are different types of imaging sensors. We have CCDs, there's a charge coupled devices, CMOS, which I mentioned earlier, your DSLR. Okay, sadly we don't have CCDs and DSLR, so we just ended up using CMOS. But CCDs have a better resolution. But the resolution we got here for this experiment was pretty good, as you can see by the result. And then we had this 8-inch NAC telescope, which had a focal length of 1200 meters, was an equatorial mount. The reason we chose one reason is obviously we have that. Apart from that, we use equatorial mount instead of mount because we are looking at the Jupiter. Then we have to go ahead and focus it and choose saturation level and everything. All of this, like we can't just point it and put it move on. So we have to look at it for some time. So we have to track it. Now, if the mount is equatorial, it is going to move in and out, and there's circular motion. So it is similar to track, but in a simple way, it will move something. So this would not be, it will make it very difficult. So the photos we get would be a little bit. So if it was mount is better than working. So procedure was to collect the images of Jupiter for a period. But you, if say it's not focused properly or there is then they get useless. So a lot of times with the service team. And then we have the data of the started taking data. We took 5 images, 5 to 6 images roughly every day. Around the same time, around like 6 p.m. to say, there was cloud one day and could not take it. Now, how could we actually be reviewing this? Right? So, one of the assumptions that I like explain later is like, but the thing is when we are looking through our telescope, this is not the thing we're looking at. We're looking at it in a different way. This is so essentially my moon is going to oscillate like this instead of me seeing an object motion. That's the orientation that we have. And we have made a bunch of assumptions, which are like the moon follows a circular orbit, as I already said. Then we have enough observations. So, as I said, right, we'll be looking at the moon like this. So, we'll assume that we have enough observations such that the moon was here at least once throughout our observation. And yeah, for all we have 4 different moons, and we're kind of assuming it that the radius and time period for all the 4 different moons are going to be different, like very different enough so that you can recognize it. And the time period of the moon is not less than 100. So because we cannot observe these things in the morning, the only time we can observe it is at night. So we have to think that the time period of none of them is like just in one day. So fourth assumption is actually kind of empirical. You can see that this is moving, and then we try to identify. Data filtration, as already mentioned. So for one day, say you have like 5, 6 data, but not all of them might properly focused, quality telescope. You can look at it like they look something like a round and not something weird, distinct shape. And you can this was like totally out of focus.
there's as mentioned earlier, we are trying since we have a finite time period, so you have to know the finite time period. You have to know where the moon is like in the first place. Now, we will just basically see where it's going throughout the motion. But if we can't focus at the moon, like to know this, we have to find the center of the moon and then move on and tell where that center is going throughout this motion. But if it is out of focus, then we don't have a circle. We have some theory, something, and it will be difficult for us to know to work on the data. Then there's this one here. It is like not fully weird up. It's not even like a circle. It's like a weird shape. Which like that's good.
So now coming to the code, we divided the code into four sets for better understanding. So to move on to the next slide, see what will happen. So we had this ruling years, 12 days images. So we first took the image. Now the code was designed in such a way that it would find the brightest spot in the image. Now if you directly put the image, what would you get? Then we see from the image that Jupiter is the brightest in it, right? So the code would essentially keep on giving you the coordinate of Jupiter and other moons would be like totally ignored. So now you had to select your object of. What we did was first put some grid lines here. Okay. Now that was your image and for that image it put some grid lines. Right? Why this grid lines? So what we by putting the grid lines we can actually get a rough estimate of the pixel values of these dots. Right? So that will help you choose your object of it. Right? So that is what we did. We chose the object of interest, we localized one bright object. And then what we did was, what the code did was, it randomly selected the brightest spot from the saturation region. You know, these cameras get saturated after one. They get more of that. So it selected and then jog. So if this is the right spot and here is the region of saturation, right? So that, right? And this code selects a okay, and then it's going to select the strip of pixels in this region, say 5, and it's again going to select a strip of pixels in this region, and it's going to plot this, as you can see in this blue dot, intensity versus the pixel number. Right? These are the pixel number, and this is the pixel of x. Right? Now,
then we chose to fit a Gaussian to whatever data we have. The reason we chose to fit a Gaussian is like, for example, say that I have some point of this is my Earth, I'm working this through my telescope. Now it comes down, and then I believe that it will be parallel with each other, the light rays. Now it comes down, it will scatter randomly. So when it's scattered randomly, it's going to give me a Gaussian distribution of the intensity versus the distance. Now, if there's one point, you're giving one Gaussian. Now, the whole Gaussian point over here. Now, each point is going to give me a distribution like this. Now, all of these Gaussian distributions, as like you can see here as well, all of these Gaussian distributions will add up to give me a final data like this, which is visible here as well. So we have a plateau kind of substructure at the top, and then it dies out. Now, in this region, there are only a few Gaussians that are in this region. So you can kind of estimate, take this as a Gaussian and then that's the reason we chose to look at Gaussians and any other.
take the Gaussian, what would mean of the Gaussian? That would be our coordinates. And then you would find the variance that would also give you the error. So what essentially happens here is you have a Gaussian over here, right? You have a Gaussian over here. Now you take the mean, take the mean of this Gaussian, this would be the center of the image, right? So we did that and we got our coordinates and the corresponding sigma, and then we did a synergy. We again put it back above that code, these pixel values, and we got the same image. So this is kind of telling that okay, whatever our code has done and found out the pixel values, it is all fine. And then this is for a better understand what activity is happening. Yes. So this yellow plot, whichever you are seeing, this is a 2D column. So this yellow plot, whatever you are seeing, is the intensity versus pixel number of, and this black plot, whichever you are seeing, that is the fit that we have. Meanwhile, you can see the output of the code gives me x, y, and then sigma n. So now essentially we have, you know, this is the movie plane with y, x, alright? And we have this Jupiter, we have the coordinates of Jupiter, j, y, j. Then we have these names, we have all the coordinates of 3D. Now, if you have the coordinates, now you can go and find the distance. Right? But now there is a problem. We have to somehow organize this data, or else we don't know which moon is which dot is which moon, right? It's so much random. So now what you do is you start to label the image every good image from left to right, A, B, C, and D. This is one day, and then that is another day. A can be anything. A can be Ganymede, IO, or Callisto, anything. You don't know yet. You just label it for our convenience, and then we proceed to find the distance. Next time you can see that you organize it that way. J, that was A. Now, for example, you have just for 3 days. That's good. Yeah. Here we found the distance of A with respect to Jupiter with time. This is time in seconds. You can see that the distance is moving, and there are negative values saying that this thing is here somewhere, some point of time is now here. We did this part for every object we had in like A, we did this research thing. For B we did, for C we did, and similarly for D. And after doing that, as you saw in one of our assumptions that the orbits were circular, right? So how do you construct a circle? It's a summation of sine and cos. So if you see a circle in this thing, it should follow a sinusoidal. So what we did was say the distance was v as a function of time is just amplitude a sine of omega t, right? Now you just take this g, divide by t, take the sine equation both sides, right? Get this equation, right? This is a straight line equation in which the slope is omega. So that is what we did. We plotted those. We did a sine inverse. We plotted those data points. We did this so that we could identify which moon was it. So like you can see those 4 yellow dots correspond to like first 4 days, and then some gray dots. So B. Now we enter the data sheet of B, and so so we have 4 set of points from A. We then have 4 set of points of I don't know 2, 3 points from B. Then we have from C. Then again we have from. So this is a full. So from this we identified the points, and then we we then fit it to a string curve. We had a code for that, and here fit, we had three parameters basically. That is our A, our omega, our phi, and we just assume some. We put some random values. This one, and then what the code did was, let's say, okay, this is something, and it just found the minimum deviation and it try to fit curve to the actual data points. So you might have heard about straight line fitting, right? So what you essentially do in straight line fitting is you have your guess straight line, and you have the straight line which the points correspond to, and you find the difference between them and try to minimize the difference. And then you find the best fit. That is what we are essentially doing here. And here you can see when we did that for Ganymede, we got a time of around 7 days, and the error was around 0.001, which is pretty low. Why is it so low? Because we have used VCM version. Similarly, the time period for Callisto was around 17 days, and for IO it was around 2 days, and for Europa it was 4 days.
And what we can see is that the error that we're getting for all of them, like the error that we can get for each the time period for each move they tends to like very low. But now, as I said, this is the first hour analysis that we did, and we got like these values somewhere, and the error was pretty low. Next, using the data, we calculated the mass of Jupiter. To get since we have the time period, we know this equation. We have the time period. We have just found the mega using the first answer that we have. We know the relative distances between Jupiter and the Moon because of the link. We know the pixel distances. We don't know the actual distances, obviously. And then we took the standard value of G. Now, to get the actual value of R, we took this actual value of R we got from literature itself. Now, from literature, we have the value of R, we have the value of omega, we have G, so that's how we calculated the mass of Jupiter. Now, to do this, we did it for all the 4 moons. So, for all the 4 moons, we have different omega, we calculated the mass using all the 4 moons, and then we got the average, and it came up to like 1.7. Now, whatever we did is this, and this is all this value. Then we saw the error, as you can see, is like pretty low for all of them, 0.0091 day. This really goes for all the time period as well as the mass. The mass itself is pretty close to it. This is very low error in general. And there's also we can try to see if it's close to literature values. These are the literature values that we have. It's we found the percentage error with the literature value is 0.29, 0.72, 0.14. So it's like less than 1% error from the literature value for all the time period, and so it's pretty close.
So what could we have done to make the process more smoother? Now, the first foremost thing was that we did not position the camera at the same position every day. One day the camera was, tilted so much. One day it was, tilted 180 degrees, and we had to sort out the glitch of the image. Because that actually gave us a real problem.
So, for example, if I am seeing this is the picture of the sky for every single day. Now, this is what the picture would be, but since I'm using the telescope to look at it, I could have oriented my telescope like this. I could have oriented my telescope like this. So when depending on the orientation, what I see would be very different. Had we made sure that we are orienting the camera such that we are looking in the same at the same angle and all, then we could have done something more with the data that we have, even though the value is close, but we have done. Using the value we have, which moon belongs, which spot belongs to the spot. Now, say that the camera would have oriented, then instead of us getting like, then we could have gotten a whole ellipse. If you map the trajectory, if you stand on the ellipse and map the trajectory, we would have gotten an ellipse. So from there is like the proper trajectory of the moon. From here we could have calculated the foci and everything. Which should, that was supposed to be a second hour analysis, but since we did not have a camera oriented properly, so we could not go.
Collimation, we could have done better collimation. Still more minimum errors. As a
Yeah, since like we had to carry the telescope every single day from on height to the rooftop. So we had like only with the telescope radars. As though we don't only with you won't get a like you won't get a circle at all. It is on weird shape. So it's difficult to fit code it. Yeah, conclusion is like we are very happy with the data that like the result that we got in general and this was a obviously pretty basic experiment, but this was the first experiment we went ahead with, and in that sense it was like quite a success. And we are also the NISER, the NAC experiments team is also, since this experiment went well, we're also planning to do few more experiments in the future to continue with that. One of the experiments that is proposed is like making a spectrometer and trying to analyze it like this that. And some other experiments that are like coming forward by the NAC. And we would like to like thank everyone from the NAC experiments team because it took a lot of effort to obviously take all the data. We'd like to thank Justin. He did a lot of work, he simulation and everything. And that's the first quarter. Thank you to everyone who was involved in this whole procedure.
Sports nights were really bad. The day we didn't get data was the most satisfying. There was cloud all time and you couldn't even see anything. Just had to sit there and wait for clouds. But yeah, thank you.
Yeah.
So,
Yeah, any questions? Sorry. Oh, which? The plane of orientation of Jupiter's moon. Are you telling about this or orientation cap? No. It won't change anything. So the figures will be because the photos instead of really had it been like this in the see when you observe it, then how do you get the car from? Now that you observe it, it will be something similar close to this. But had it been like a proper this image which we have here, then instead of that would be like I'm not talking about the orientation of the orbit with respect to the plane of the orbit of the moon. Yeah. Are they the same? Yeah, what effect does it have on the plot? Yeah, so what you're let me get it. So what you're trying to ask is are this IO Ganymede in Europa the same orbital plane? No. I know that okay. They're the same orbital plane, but with respect to our field of view. Yeah, you're saying it is a bit tilted like this. Yeah. So what effect does that have? Yeah, not much actually. When I showed you the data, right? You saw the Y values, Y coordinates. They weren't changing much, just going up and down. So you could have. So that was another assumption we had made that they are going straight. It was not deviating much. So there is a slight angle between the plane of the solar system and the plane on which these moons are. Yeah, yeah, that is pretty much very short of the that was much. And actually, we completely disregarded the orientation. We always oriented it in this way. If we are, if the moons were supposed to be like this, but we are going to be turning our camera lenses on the moon, so we are always seeing the straight line. We are not seeing the actual competition. I mean, like, if this is Jupiter and the moons, we are seeing them as points, right? They would be moving like this also, they would be moving like this also. So we were doing anything. We just brought them to a straight line. But that did not affect because ultimately we are doing a distance analysis. We are finding the distance. But had we like distance was again because of orient. Theta. Yeah, but I told you right, the Y was very so you could ignore that. Any more questions? Can you go to the slide when to very good two pictures of the motors? ABCD one? No, when you took two different
image of two different days and you put it on one slide. That's it. Are you asking about labeling one? Yeah, ABCD. Behind that. Answer. How do you like in the first one you took ABCD randomly, but how do you on the second picture how do you know which one is A and which one is that is what we do. So you took it like in the second picture also you took it randomly. Yeah. That's not random actually.
So it's crazy. We randomly label them names since we don't know who. Then we went ahead and like since we then doing a simulation and everything, we started them. And now from here we can tell which one like which dot corresponds to which one, and then we so the second image also we just told that okay from left side whichever is the first one is A. The second one is B. Third one is C. We don't know. And then using the data we use. So when you are taking how you are calculating positioning, you are taking the most bright one of the brightest saturated spots, right, and taking the center of the Gaussian, right. So why don't you do the same for the bad hazy images? The hazy images won't give me a Gaussian kind of surface. For example, I'll show you. For example, here this is not even a circle. So if I try to put a Gaussian, I'm essentially not getting this curve in general. If I that in a circle, I get some weird curve. Have a something like this maybe. So doing the same thing there would not give me the proper one. Or what if the image is not focused properly? Like one of the images yeah, like this one. Yeah, again here that's identical of both. Identifying is still fine, still not like a proper stuff. Jupiter would not be a problem actually, but you don't know which what. So you mean to say that you cannot say whether that smudge, color of smudge is actually a moon, or is it because your sensor has noise, or is it a noise? Okay.
Yeah. The only in your final data, go to your final data. Last where mass, yeah. Okay. So you're saying because of your while taking your capturing pictures because the camera orientation was not the same. So is that why your Jupiter mass like uh, does the actual value of mass lie within your error range? Yeah, but does it lie within your error range? It doesn't, right? Yeah. So that's the. So then should you for error calculation, what did you take for the mass of Jupiter?
No, see, there was you see capital law there is this R cube, right? So for that,
Let's go back once. You're more more back where the formula was there. Yes.
so you have the R cube, right? So that R cube, you need a K factor, which we are doing this by size of Jupiter. Like we are equal to one pixel is how much? We found that, right? Okay. Now we have the deviation sort of. Like I told you that this standard deviation was my error, right? While determining the center of our image. So now that one pixel would have that error, plus or minus.
So you
That error will be propagated in that.
that is fine. But for your RQ values initially, you took literature values for equatorial radius and the polar radius. So, but to did you consider to calculate the relative distance or radius of Jupiter? Did you consider using the telescope itself,
No,
taking the telescope value and optically measuring? Like let's say if you know your telescope's what both angles, declination and that, and that's all.
Yes, this one is the first thing about identifying A, B, C, and C. The labeling them randomly in the first instance. But we know that the sizes are different. The moons are different, right? Okay. Different size. So can we not use the relative intensity of?
Yeah, that was actually thought that was actually thought of in the beginning that since they are like four different moons and they will have different densities, so we can assume that the telescope can tell what intensity it is. So the brightest one will say correspond to one and all. That was the thought, but then when doing the observation, since you saw, for example, if you see this image. Yeah, if you see this image, here you can see all the colors and everything of the different. The next image when you see, it was all white. The reason was all the images that we got were actually saturated, like the number of photons that could be taken was saturated with the CUs. Can you see that actually happened to all the photons. That was the issue. That was one of the that we could not do it, all the.
Let's search.
So we could not distinguish. Yes. So I mean, in all of them, you cannot identify the relative intensity is not unique. The picture that you take, it's not uniquely defined.
Had we had like a more sensitive, it was possible. It was all the evidence we got. What was possible in that CM was in saturated. In the saturated.
Basically, the people who took the data, kind of setting up the telescope and putting the data as a practice run. So they were practicing on setting up the telescope, and they were using the telescope first time. So the gain was too high. That is so with lower gain and lower exposure time, it would have been possible. But my point, I cannot explain things clearly. So the problem with that would be, I mean, where.
Yeah, that could yeah. Yeah.
So if we consider the luminosity, would it be like even if the collimation of
Realize that it's orbiting the then he realized
this ORI and OCD is actually using just as we did ABCD, right? This is west and that is east. We can work. And there is some
yeah.
like here are pictures when one of the movies behind Jupiter. There are also three of them.
Yeah.
So in that case, how is it able to pinpoint the position of the moon? What do we do? We just don't have that.
That's we can't wait for it. Yeah, just for that particular reason.
But we'll see the next day or so. After a few days, it will again emerge. That is when we can again continue. Okay, this point went here.
But that would affect the line in the end that they are
Ultimately, fitting the curve, right? Even if you have 3 points, you can essentially fit a sine curve.
But again, you'll
one of the data would be less obvious.
even your missing data wouldn't matter because at the end of the day, if you have enough data, all of them have different time periods. So when you put them on the graph, it will become quite obvious which set of data belongs to which set of because over the time. Because again, you're taking them on the same time, but they'll be on different points. It becomes more complex if you have enough data points.
Yeah, and you go to the slide where you plotted the line images. This bit. No, the very no line plot line. So in this from this graph, we can identify each move. So now there was 5 elements.
Okay, this is okay. I'll tell you what happened. The plot that this is not the plot that we originally planned. Okay, this is the plot that we Should have put the distance and we put the straight lines. We have this. So we took the distance and we just plotted distance with time, and we actually got something like sine curves. Like since the image could be like 180 degrees different, since we just wanted a straight line, so we just put sine curve and for 4 moons we got like different sine curves. So that's how we identified.
And it's not long time. So we see the time that you have a different variable and find it. Okay, now so we go on shifting this. Now which line is which point lies on it? So some point is say this is in between somewhere, right? Pi lines with the fifth line. So you again shift it by n pi, like you shifted pi, will it go and match some line? You shifted it by 2 pi, will it go and match? After some 6 pi, it might go and match. Okay, these are points. Because there is a phase of time.
But then we can do it. Yeah, it was the same.
I want a couple of comments. When to really label your cis more.
Yeah. Yeah.
I have also a question. So you mentioned that is taking so like, what part of the how the construction happens does that cause that in the sort of direction? If you want you might say global and local for
When we have the we one axis is going like this, and the other one like so. Just like this. That's how the equatorial form works. But in the as it is about one of the axes like this, straight in this plane, and the other axis like this. This thing. So when we like put it in a motor, it sends it to only like this or this. So and it has to like go in a circle. So to approximate a circle.
what is the resolution?
Yeah, like for example, which is but since the resolution that this thingy that's there is very small, so it essentially does a good job.
Oh, so you tried and
The dimensions is good. But we did that, but we use a editorial mapping.
really wanted to know whether we've talked about this for like since we were part of the astronomical right from the start that it's the quality is not as good when it goes like this. I wanted to know if you have like the time resolution.
11 inches like pretty good at tracking it.
We should still try.
Yeah, it's try this.
Actually, from the data plot, the data you were starting right was plotting the sine curves, or you started.
We use the sine curves.
You did the sine curves and then came to the straight line because the straight line had the amplitude dy. No, we did the straight line. We did the straight line to identify the points. But then how to take the value of sine? Okay, yeah, that is. So.
Okay, yeah. We made, I told in the beginning that making an assumption that on each day, we have such an observation such that the moon is essentially going at its speed.
So you're assuming that the value of capital A is equal to 1.
No, we take one of the data, and say I have all the data, I got the maximum amplitude for one data. Now I take a data, I hit the line, and from the line I got which moon it belongs to. Now for each of the data points, on each day, I remove the moons. Now say the next biggest amplitude that we got is like, we do this for like all the each of the moon and each of them. So the obvious assumption is that in one of the observations, it is like going.
So far they have been the same.
I can't sorry. Sorry. So the idea was we are assuming that in one of the observations, the moon is going to at least one of the extremes that we have. Now, the say moon A has the biggest radius, then we take that radius as the like that one as the amplitude for our fitting. Now we have this amplitude, we make the line plot that we have, we find the moon, and we remove all the data points that belongs to that moon. Now, so the maximum amplitude value is also. You're taking the leftmost as the aim is bigger. No. The aim will keep changing. That the day one, I have the not all the days, I have the maximum amplitude for all the possible days. I take that as moon A. Okay. Now for moon A, and I divide it by all of this, like when we get a time that we have the A's and B's, and then we plot the lines that we have. Now we have the line from here to identify which one belongs to this particular moon A, and we remove like all the lines over here, all the points over here. We remove all the data points that correspond to this particular moon. Now in our data set, of whichever data is there, A is gone. Now we look at the next biggest amplitude and for the next moon, and we do the same and then how we everything's on it. It is not. A is not fixed. You're taking the leftmost known as A. So A is keeping on changing. I got your question. The distance which we calculated, we have a table of all the distance. From that table, we see the maximum distance. First maximum is the distance of A. Fine. You have each day for distances, and you have it for 20 days. Out of this whole box of days and distances, there will be one distance that is the maximum. Yes. So if you divide the distances of all of this by that one, so at that point you have a sine inverse to be handy. So sine inverse will be extreme there. Everywhere else it will be small. You do the straight line plot. Do all the n pi shifts. So there, the ones that are inner moons will always, like if it's an inner moon, has a radius of 50 pixels, and the outer moon has a radius of 500 pixels. In the inner one, it has very small amplitude of the oscillation. So if the sine inverse will only go through, say, sine inverse will vary between point, let's say it goes to minus 0.1 to 0.1. It will not go up to 5 by 2, minus 5 by 2 to 5 by 2. Right? So this will linger in a very low value, but there will be that one moon that corresponds to this that does a full sine, and that will have the straight line curve. So once that straight line is identified, all the others don't matter. Those we know which moons are giving me exactly the points that match to the straight line. I will subtract all of those points from this entire table. Then I will take the next highest value, that is the next moon. Do the process again. So actually, this table can see the maximum. So this is right. I don't think I've opened it correct. Yeah, there is no. Go back up. Go back up. Still there. Yeah, there can be 1,045 is the maximum. You can take 1,100 as the maximum value. If you are in the whole one, then you understand. And here the points have been color coded. Yeah, like yeah. The moon that they correspond to, like basically these are the points that fit to that. Like for example, in all of them are labeled random. Now these are the points, the data points that correspond. The yellow went to D and there were 2 points in D and then it came back. So the progressive find from the Shreya. Yeah. And then she's then find the extreme ones. Only ones. Yeah. But after we got the Shreya, then we find after that, then we went to the one. Yeah. And the maximum estimate that this one is on P or it can be from the B or C or that slope is the slope that determines which point belongs to the The rest will not follow as that slope at all. They will be in a completely different place. Yeah. So there will be a completely different shape. That is going to be a different.
So you want to shift phi based on one. All of them will go on, or all of them will come on. The phi is same for all points. Like the phi is same for all points that belong to the same for same. So whole line go for whole line. The bottom ones they will also do the same. Meaning the other ones. Yeah, the other ones, the data that does not matter to this line, they will also all go for one way. They all cannot compress and form and this one. All of them should match the entire line. You cannot match at one point. Be like that. So what you're saying is we have the freedom pi. I should let's say there are 2 points. In between phrase, they come close to the line. Right, that is the whole problem. So out of them, which one do I choose? So show the data table. Yeah. No, if you go to the data table, if you see sixth there, so there is the orange of 187. 187 are pretty close by. Which of them is the orange moon and which of them is the other one? How do we determine? So there we employed whichever is closest to the straight line made by the other points, that is the one I will. So that is the movement. You have to make it first.
Yeah. In that table, we have four of the pieces of how do we identify which images are
How did we identify that? Okay. So what it actually means is that you get an idea.
which is the
So my image is if one day you will showing the movie with there. Next day if it is a film, it will have done. But after that, the day after this one, again it would be back there. So essentially it would be positive first, then it became negative suddenly. Then again it became positive.
there is one thing, but
And we know that it is not less than 1 per day. No orbital greater less than 1. So in one day it cannot change so much, right? It cannot suddenly go negative and then come. But that is how we get.
the other thing like we did is was like when we make a sign chart, we did not make like for one of them. We just for both of them we have a sign chart like this for both the sides. Now if it belongs like if it goes to either of it could have gone if it was flipped, it could be here or here. So depending on that, we still take it. Still take it. Yeah. Yeah, and in the reality also it was pretty close at the start.
So the why that. I can see why that very short. Each stage who was buying on it, there are around 39, 29, 31, 41, 32. Out of 48, that's all. Was that's like up to your real like any regarding the realignment is going to only make so basically with respect to the plane in all of these moves, there is a very small shift. Right? So if you build the whole thing with respect to the plane of all the moves, so if you have 4 dots, join all of them or try to fit as lane and join all of them. There the shifting will still be strong. That is our main thing. We're not making that in the camera it's only movies. So then where it is if it is large, then it will matter. Okay. Then what happens is the radius we have calculated is not the true sinusoidal length. So that is only the component of it will be a sinusoid, other component will be the phase shift sinusoid. So that issue will be there. So we have gone ahead with the assumption that this is small enough to ignore the vertical sinusoid. where we can, in principle, do an experiment to determine the others, and you would also use both of them and get more accurate results. But we haven't done that. For this also, we would need to position the camera at the same position.
No, you would have gotten the LFC.
You would have got them. Right now, I have some ideas to do that transformation. Way to complete it and see.
Anything else? Yeah, thanks to Pankaj.
Yeah.